number 11, we are finding another composition of functions here. H is on the outside, R is on the inside. So when I look at the composition, I want 1 over something plus 2, and that something is going to be R, so that's x minus 2 over x plus 3. And then I want to go ahead and find a common denominator. So I'm going to multiply that 2 times x plus 3 over x plus 3. And let me go down a step. So 1 over x minus 2 plus 2 times x plus 3 all over x plus 3. And so that will put the x plus 3 up top. And I get x minus 2 plus 2x plus 6. Alright, so x plus 3, 3x plus 4. Okay, so that's my composed function. Now the question actually asked for the domain of this. So in the domain, I want to look at the inner. Alright, so looking at R, I'm going to look at its denominator. So what number can't I have in that fraction? I can't have negative 3. Okay, so that's going to show up in part of my domain statement. That negative 3 is out of there. Looking at 3x plus 4, okay, that one, I want to figure out what it can't be, and that would be that x cannot be negative 4/3. So that's what I want to say in my domain statement. It might help if we look at a number line. What comes first? Negative 3 and then negative 4/3. So when I write this out, my domain is going to be negative infinity up till negative 3, negative 3 to negative 4/3, and negative 4/3 out to positive infinity. So it's going to have all three of those pieces in it in the correct order. Alright, next piece. That symbol, r to the minus 1, actually means the inverse of. So when I go back to r, let me copy that over. So r of x is x minus 2 over x plus 3. So to find the inverse, I am going to replace the r of x with y. And then I'm going to interchange x with y. So x equals y minus 2 over y plus 3. Okay, so now I want to get y by itself. I want to solve for y. So I'm going to multiply by the y plus 3. Now in this case, I've got y's buried on both sides. So I need to find a way to separate the y's and get them together. And so it makes sense to distribute the x in this case. So xy plus 3x equals y minus 2. Sorry, y minus 2 as opposed to what I just wrote. Then I'm going to bring the y terms together. So xy minus y equals negative 3x minus 2. I'm going to factor out the y's. And then I'm just going to divide. Okay, and then that is actually the inverse of our original function. Okay, so number 13, we got a lot of different properties that we can pull from to sketch a graph of this. We're going to start with end behavior. So if I think about this, this looks like an x cubed times an x squared, which is an x to the 5th. So an x to the 5th, it's an odd function, so it would be in the long run it would go in the first quadrant and in the third quadrant. All odd functions do that. The other thing, or other things that we can find the Y-intercept. So if I find f as 0, I get 0 minus 2 cubed times 0 plus 3 squared. So that would be negative 8 times 9, so negative 72. So I know there's a point 0, comma negative 72 in the graph. I also know about multiplicity. So here if I look at each of the intercepts, let's see, that's x equals 2. So at 2, 0, there's a multiplicity of 3. And at negative 3, 0, there's a multiplicity of 2. All right, so I'm going to put all these facts together, try to sketch a somewhat reasonable. So my scaling is going to be really off on my x and y axis. It's not going to match, but I can see that it crosses at 2, and it crosses at negative 3, and then way down here, we're going to pretend that that's 0, negative 72. So we're going to have this really scaled up y-axis. And then I just got to remember my bounce and wiggles. So it crosses at 2, it's got an odd multiplicity, so it's got to have to wiggle through it. And then at the negative 3, it's going to have to bounce it. And let's see. And then it's going to have to go on the first, go on the third. And I know it's going to have to eventually get down to that y-intercept. So I'm going to sort of fill in the blanks and connect all these lines. So my graph looks like that. Again, it's kind of skinnier in the middle because it has to go all the way down to negative 72. Over here, with g of x, it crosses, let's see, so we got, let's do same sort of end behavior analysis. I have x times x squared, which is x to the 4th, which means it's got an even multiplicity, or an even end behavior. So it's going to be in the first and the second. The y-intercept, so g of 0, would be, well, let's see, 0, so it would be 1 times negative 1 times 4 squared. So that would be negative 16. So at 0, negative 16, I have an ordered pair. And then I've got my multiplicities here. So I've got one x-intercept at negative 1, 0. I've got another one at 1, 0. And at negative 4, 0. Now that negative 4 has a multiplicity of 2, which means it's a bounce off of that number. Okay, so let's put all these facts together. Starting with my x-intercepts, so negative 1, positive 1, negative 4, right there. And again, I have a little odd scaling on the y-axis so I can get that point included. And let's see, so it's got to bounce off of the negative 4, but it's got to go out on the first and second. So it's got to bounce off there. I know it's eventually got to get to the y-intercept. I know it's going to have to cross because it's not an even. It's going to cross there. So I'm going to fill in the blanks. So it's going to have to come here. It's going to turn around at some point, come all the way down there, cross over there, and look like that. So in general, it's a good rough estimate on what that picture looks like. Okay, in this graph, we got a little bit more work to do to get back to where we were a second ago. I can start with end behavior. So I know it's going to look like a 4th degree. So a 4th degree is first and it's even, so it's got to be first and second. I can evaluate h of 0, and I can very quickly get the y-intercept of 4. So I know it crosses that. But what about the x-intercept, right? Well, this is where rational roots theorem kicks in. So that's where I'm going to have to do that whole PQ process. So let's see. I want to look at the 4, make a list of its factors. So 1 and 4, 2 and 2. And then look at the leading coefficient, which is 1. And there's only one way to get it. And so my possible factors are plus or minus, and then just take each list of the top list divided by the bottom list. So 1 over 1, 2 over 1, and 4 over 1. So it's plus or minus 1, plus or minus 2, plus or minus 4. So we got 6 choices there. And I go ahead and set up my synthetic division. So x to the 4th, x cubed, x squared, x in constant. So 1, -2, -3, 4, and 4 are my numbers. And I'm just going to guess a number. Let's try 1 out of the list. See what happens with 1. So drop the 1, multiply, add, multiply, add, sorry, -4. Let's see, multiply, and I get a 0 there, but I get a remainder of 4. So that didn't work. So I know 1 doesn't work, so I have to try something else. Okay, so since 1 didn't work, let's go back and let's pick another number. Let's see, I could go with -1 or I could go with 2. Let's try 2. Again, I'm just guessing a number. So drop the 1, multiply, I get a 0, that's a good sign. I get a 0 there. So -3, okay. Gives me -6, -2, -4. Okay, so that worked. Okay, so 2 works. Now, I know 1 doesn't work, but there's still a possibility that there could be multiplicity here. So I'm going to try 2 again and see if it still gives me a 0. And if it doesn't, then I'll just guess another number. So we drop the 1, multiply and add, multiply and add, multiply and add. Okay, oh, so there is a multiplicity there. Alright, so I got 2 twice. And then this thing translates into x squared plus 2x plus 1. And then I just want to factor that. So once we get down to a quadratic, then we're going to use our factoring skills. So that actually factors into x plus 1 and x plus 1. So this thing in factored form is x minus 2 squared and x plus 1 squared, which means we've got 2 multiplicities. Okay. So it crosses the x-axis at 2, 0 and at -1, 0, both with a multiplicity of 2. So it bounces off both of those. Alright, so let's go get our other numbers. We got an x-intercept of 4, or y-intercept of 4. Okay, sorry about that. Alright, so 1, 2, 3, 4. Hey, I don't have to have weird scaling on this one. That's nice. We said it crosses at 2, crosses at -1. We also said it's even multiplicity or even end behavior, so it's going to have to come out first and second. And we also said that it bounces off of this. Let's see. Okay, again, I just realized something. Aha, here's what I realized. I said it's 0, 4, and I'm graphed it at -4. Alright, let's try that again. Alright, so it bounces here, it bounces there, and it's got to go through that point. So if I just connect all of this with a smooth curve, so it should look about like that. Okay, in this rational example, and we actually talked about 3 different cases, seriously looking at top heavy, bottom heavy, or the same exponent. So even though this is a body heavy example, bottom heavy one, you want to go back and review the other types that we've seen in the course. But I'm just going to make a list of my facts and then we'll come back and graph it. So starting with the vertical asymptotes, I get by looking at the denominator, and that's at x equals 3. The x-intercepts I get by looking at the numerator. So if I take that and set it equal to 0 and solve, then I get -3, 0. The y-intercept I get by evaluating it at 0. So r of 0 is 0 plus 3 over 0 minus 3 squared. So that's 3 over 9, so that's 1/3. Okay, so at 0, 1/3, it crosses the y-axis. It is a bottom-heavy rational, so that would make it y equals 0 for our horizontal asymptote. And then last question I want to kind of ask is, does it actually cross the horizontal asymptote somewhere? So does it cross the HA? And so I want to take the number that's the horizontal asymptote and set it equal to the equation and see if there's a y value that it generates. Okay, so I'm going to multiply 0 by x minus 3 squared, which is going to give me x plus 3. Now, in doing that, I am assuming that x is not equal to 3. So if this process gives me the number 3, then I know it's not going to work. Plus, there's a vertical asymptote at 3, so hopefully I don't get that confused. But I do recognize that I get a negative 3 out of that. So does it cross it? Yes. And it crosses it at negative 3, 0. So it actually crosses it at the x-intercept. Alright, so let's plot what we know, and then we might have to come back and set up a table of some type. I know that there is a vertical asymptote at 3. So at 1, 2, 3, I know there's this VA there. I also know there's an HA at 0. And I know that it does cross it at negative 3, 0. So 1, 2, 3, there is a point that it actually crosses the graph. Okay, so now a couple of questions I have. Does it start there or does it start there? I mean, is the graph above or below at something past negative 3? Same question afterwards. If I figured that out, then I could sketch in at least the left half. And then I don't know if it's above or below on the right half. So there's a couple of mysteries I got to go back and solve. So let's see, let's go back to negative 3. So if I plug in something on the left side of negative 3, something like maybe negative 4, that will tell me. So if I go negative 4, negative 4, well, down below I get whatever number I get, I'm going to square it. So I get a positive number down below. Up above I get a negative. Alright, so overall that means I have a negative result, which tells me my graph has got to come this way. It's got to be below, not above. Alright, so what about between negative 3 and 0? Okay, so negative 3 and 0, same trick. Let's pick something, sorry, negative 3 and 3 actually. Let's actually try 0. Let's plug 0 in there. Oh, I didn't put the y-intercept in there. Duh, that would have helped. That really would have helped speed this up, wouldn't it? So the y-intercept is right there at 1/3. Well, that already tells me what's going on. It's got to go from that point to hit the y-intercept, and I know it can't hit the x-axis because I already figured out where it crossed it at, so it's got to keep going up. So that part of my rational looks like that. What about over here though? Past positive 3, like at 4 or 5. So let's do the same trick we did a second ago. Let's put a 4 in there, and I get a positive. 4 plus 3 is positive. 4 minus 3 is negative. So positive. So I get a positive result, which means that it's above. It's got a hug above. So that is what my rational function looked like.